I'd like to welcome Professor Ger Dooley, who will present on CRIS.
Yeah, so thanks a lot, Niall. What I want to go through is the understanding of what CRIS does. We're primarily robotics and intelligent systems. This is what the team looks like. So I guess there's two co-directors and there's another primary lecturer or professor, which is Thomas New. So the three areas that really follow these three professors or PIs within our centre is myself in aerial drones, Dan Toll in underwater robotics, and then Tom New across cybersecurity. So when we look at the centre, most of the other people then are funded through research. It's not academics. There's a few other additional academics, but primarily it's mechanical engineers, electronic engineers, aeronautical engineers, and it's all research money that we've won through research grants. So when you look at the team, we spend about, I'd say, $2 million every year. So to keep that team going, we submit about 15 proposals or even 20 proposals per year. So we're continuously putting in different proposals in each of those three areas. This is our stats over, I'd say, the last 10 years, and even this is only really the robotics side. It's not including Tom News. So we're about 24 million over 10 years, so you're about 2.4 million a year. Outreach then, I guess, in terms of surveys, we do a lot of surveys with different people, be it through the funding agencies or through industrial links, then we're continuously in the field. Most of the stuff that we develop then would be higher TRL stuff. We do some low TRL stuff, but then try and bring it towards commercialization. So we're targeting high impact stuff, looking at working with industry to roll out, say, software developments or hardware developments or something in between. Publications over those 10 years is about 500 publications. So it's quite significant. I guess when you look at the research centres, you know, most of the stuff that gets showcased in UL is primarily through research institutes. We don't belong in a research institute. So there is a lot, and it's great to get a showcase and to actually showcase what exists at some of the centre level within UL. Here's some of the drones. So what I want to go through is some of the examples really that we do. And when you look at some of the examples, it's all in the field, but what's backing up this then is algorithm development, a lot of systems that we develop before we go into the field. So some of the systems that we develop, you could be developing for a year, some of the systems, and then you roll it out in an initial test and demonstration. You develop it further and bring it to a second test in the following year. So it's all, say, in-field developments, work with industry and trying to develop impact with those industry. The top one is your typical multi-rotor drone. So when we would have started, we would have built a lot of these systems in-house. But I guess when you look at the research landscape, you know, it's more economical then to use off-the-shelf components. So a lot of the stuff we use nowadays would be off-the-shelf, and then we embed our own, say, payloads, our own embedded controller systems, and then we're really developing really perception systems that sit on a lot of these field robotics. The bottom one then is us flying Northern Ireland up at 1,500 feet. Again, for a research institute to say drive into some of this stuff is quite unique across Europe. The infrastructure we have and the systems we developed are unique. It's recognised across Europe and across the Irish landscape. So the bottom one then is a company we work with in Shannon. They manufacture this drone. It's 60 to 80 kilos drone, and I'm the, say, authorised person within UL. UL is an aviation operator. We operate drones, and we have a licence then as an operator through the Irish Aviation Authority. And we have about 12 pilots, or 14 pilots within UL, which will be licensed then to fly these drones and also the multi-rotor drones that you see. In terms of payloads, we do LiDAR systems, multispectral systems, hyperspectral. We do, say, RGB systems. So depending on what we're actually developing for the use case, the payloads could be quite different. Going to the projects then, I'll just go back there. This one is GARD. It's a DTF that I have. It's a $5 million project working with a couple of industry partners and a couple of academics across Ireland. It's industry, or it's EI based, so it's primarily Ireland. Primary partner there is Irish Defence, so it's Navy. When you look at Defence, they operate ships for fishing incursions, I say, drug interdictions and stuff like that. So it's primarily drugs and fishing. But you can imagine trying to move these vessels over long distances. You spend a lot of CO2. You burn a lot of salaries in people. And again, it's not really economical. So when we look at this, you can deploy, say, large drones. You can have vertical takeoff and land drones from these vessels. You do your survey, which is automated. And then the automated results come through the cloud back to the Navy headquarters. So we're working with the Navy to roll this out with them, with Atexin, which is a company in Shannon, to try and drive this forward. So instead of doing your survey analysis via moving the vessel, all you do is you launch 2 or 3 of these drones, you do your survey, and it can be 100 kilometers in an hour, so it's quite effective. This drone flies for 6 hours, so that's 600 kilometers. However, regulation comes into play. Now, not for the Navy. Navy can do really what they want so long as they're communicating with all the other agencies. But when I want to fly as a commercial entity or for commercial people, even in, say, climate action, so surveying habitats and stuff, I need to have a license to be able to fly 100 kilometers or fly 200 kilometers. Because now I'm flying in airspace. I belong to the Irish Aviation Authority, enforced through IAA and enforced through EASA. So this is our detect and avoid system. And really, it's an encouraging monitoring system. What it does is around the drone, we can see any airborne asset that flies into our airspace out to 3 kilometers. And we do that through thermal imaging. We developed a number of algorithms, be it, say, the first one would be, say, a machine learning algorithm to identify a target at distance. We then crop the image and we do some analysis on, say, optical flow to try and assess the speed of the target. And then we do a bunch of weightings to understand whether it's an incursion or it's not an incursion. So what we're trying to do is increase the robustness of that. This is actually a test. So there's no training data here, it's a test data set. We rented a helicopter, bottom right, and that's the transects we've done. So we did up to 3 kilometers, 3.2 kilometers distance. And you can see on the RGB, it's very difficult to see it there on the right-hand side. Our system easily detects it out to 3, and we believe we can even get that out to 6, 7 kilometer distance. That's quite effective for, say, the industry. When you look at European Union is driving what's known as urban air mobility systems. So eVTOL, passenger drones, cargo drones. And what that's around is smart mobility, trying to get, say, vehicles off our road, but also to make mobility easier for people in general. So the core of that, one of the core attributes that you need to unlock that industry is detect and avoid. And it has to sit on the drone, and that's what we developed and showcased. And we're driving that forward with a number of industry partners to try and bring that into a product. Second one here, AI birds. So when we look at, say, offshore wind has to do habitat analysis. So if you want to do an offshore wind farm here, you have to have at least 2 years of bird survey data. Now that's bird and mammal data. What they do is they'll survey it with a Cessna, and you can see the little dots there. They're birds, yeah? It's hard to see that against the, say, waves and all the ocean. So what we developed is two approaches. So we do a machine learning algorithm on the drone that detects the bird, yeah? And then once we detect the bird, we use a second payload with a much higher zoom to get a good quality image of the bird. So instead of, say, a large field of view, which is, say, 10 centimeter GSD, we're going down to, say, 4 millimeter GSD. And with that, then, we can do full classification on our data sets. Now, what they do in industry, they manually analyze all this data sets. So when you look at some of these data sets, this is what they're doing. They're looking at, say, 10 centimeter GSD. So these are actually whales. And again, the quality of the data isn't good. So what we're trying to do is bring in machine learning algorithm into this industry, not only to automate and produce the outputs, but also to improve the data set during the flight. So this is what we end up with. Third one is around infrastructure monitoring. So when we look at, say, EU, another critical part, what they're looking at is critical infrastructure management and enforcement. So really around ports and stuff, they recognize ports as being critical infrastructure. And this project, it's another European grant we have. It's using autonomous surface vessels in conjunction with drones to do survey of ports. But again, also when you look at offshore wind, it's also critical, and it's an area that we're exploring. To be able to launch drones from shore, transit, say, 20, 30 kilometers, inspect your wind turbines, your substations, all from shore and return back within the hour. You know, you're not looking at mobilizing a vessel for 3 days and getting crew together to actually get out and then end up with some weather issue. So the weather windows are quite narrow, and you can end up with, say, smart path plan like this. So instead of doing your traditional path plan, we understand where the safety is, where the target is, and we do a 3D path plan around that. That's also automated on board on the drone itself. So then you end up with, say, a demonstration like this. I'll try to skip some of this because I know time critical, try to move on. So this is our first stage. We do a high level and we understand the environment, we do perception, we use that mesh then to generate a path plan around what we actually want to inspect. Because then we want to categorically get a close quarter inspection on the asset that you're using. So ASV, fully automatic landing, again it's slowed down just to show you how it's done. So this is using machine vision. So throughout the projects we would use machine vision, machine learning, and other things, data analysis, to be able to do some of the robotic actions that we're actually performing. This is what you end up with is just your stage 2. You can see the plan around that, and it's quite good in terms of avoiding infrastructure, which is lampposts and stuff. So we can automatically generate the 3D path plan, and we can execute it automatically. It's all done in the cloud on the vessel. There's no human interdiction here on this system. We also do some close quarter detect and avoid just to make sure that we're not actually going to collide with the unit as well once we're flying. And this is automated crack detection. So trying to automate the processes then in understanding whether there's an issue on the infrastructure. In terms of impact, like we do a bunch of projects, we develop our system, we work with industry all across Europe, we work with, say, partners, but then we also do a lot of local impact as well. We work with the Navy to try and roll out some of their systems, improve the way they execute their surveys. We're working with ATEXIN. I guess we would have been one of the first people ATEXIN worked with in Ireland. They started off with 4 people, they're now at about 50 people, and in a couple of years they'll be at 200-300 people. So they're growing at an exponential rate. We would have supported them along that track. They've taken postdocs from me and other students as well from me, so we're embedded really with some of these companies. We work with ESB, that's their own university there in terms of LiDAR mapping. ESB then in terms of power line management, power lines infrastructure management, and we would have generated the middle right there is a drone airspace that we worked with IAA to establish for drone testing. It's off the East Coast. So we do a lot of impact. In terms of underwater then, running out of time here. So underwater, this is our primary asset for underwater. It's a 2,000-meter underwater robotic system. And what we developed in CRIS under Dan Toll is a control system for this. So in automation, in ROV world, subsea inspection and intervention, these are really construction vehicles. So you want to build a wind farm, you need a ton of these, you need them on vessels off the shore, and you need experienced pilots. So when we looked at that, we developed smaller systems in-house as well to replicate the control systems. So we have both intervention and inspection. And this is the control systems that we developed. This is developed over a number of years within CRIS. It's known as Ocean Rings, with Dan Toll leading Nordic. And you can see what we're actually developing here is automated control systems for subsea. How they operate within the industry, they have a joystick and they're working off of feedback off a camera, which is very inefficient. They get pushed off course, they react, get back on course. What we developed is control systems for all this and an automated, say, HMI and system around that. And what we've done since that, in terms of just control, we then developed a perception system similar to what we did for aerial that get embedded on this. This is, say, looking down at a World War I submarine and transiting to the left. So again, once you have good control on your system, good automated control, that has an effect on the quality of the data that you get back. So you can see the quality. This is real time. It gets cleaned up again in post-process. You can clearly see, you know, what you're actually imaging there. And then you can do infrastructure analysis or just bathymetric output from that data set. In terms of photogrammetry, you would have seen photogrammetry for, say, aerial. We also do it for subsea. Again, control comes into play. This is some of the systems we would have ran for photogrammetry. This is a Type 21 submarine off the north coast of Ireland. And when you look at this, you know, it's not just infrastructure, it's not just bathymetric. Really what we're doing here is climate action. So we're trying to assess what habitats live on these shipwrecks. We have thousands of shipwrecks off the Irish coast, and they attract biodiversity in terms of fish life, in terms of marine life and whatnot. So what we do then is we can use these shipwrecks, we can develop baselines around these, see what's there, come back in 5 years and see how it's decimated. And we can try and associate that then back to climate action. What effects that has on the area, because then what you're doing then is you're sort of assessing that whole area for this shipwreck, for that region, and you can develop a model around that to say how maybe some of these climate actions has affect those areas. And we're using shipwrecks because shipwrecks attract all of these biohabitats. Again, shipwrecks, we can also do laser imaging. So what you've seen for, say, LiDAR, you can also do LiDAR imaging subsea. And what we do here is we move a laser line across the infrastructure that we're doing. So moving on, these are some of the projects that we have in play. So I guess within CRIS, we would have, say, 10 to 15 projects at any given time. So we would have European grants, maybe 5 or 6 projects, and then 5 or 6 national projects, and then 5 or 6 smaller PhD projects at any given time. So there's a cohort of different projects underway. We're also offshore. We get access to some of the research vessels. This would have been last year on the RV Tom Crean. We were off the east coast on a lighthouse, so doing infrastructure development, control development, habitat analysis, assessment development. And then this is another one we work with in SEI. We have a project then working with some Portuguese partners looking at, say, wind farms off the shore. So again, infrastructure analysis around wind farms. And again, when you look at, say, you know, people that do this, you know, research institutes that have this capability to get on floating offshore wind within Europe. There's not many sites like this. So we are unique across Europe to be able to assess and develop some of these platforms. So moving on, guys, sorry. I need to finish out with the cyber, otherwise Tom will kill me. So the third focus area within CRIS is the cyber security and networking communication part. This is led through Professor Tom New within CRIS, and it's another significant area for research in terms of impact and output within UL. The Cyber Shock project is funded through the SFI Challenge Fund, which you're all familiar with. This is led through MTU in collaboration with Tom here in UL. So Cyber Shock aims to increase the resilience of Ireland's national digital assets and digital critical infrastructure against digital shock event in the form of a cyber attack. So we're all familiar with, say, recent cyber attacks within the public sector. So this is really trying to target those attacks, develop the knowledge base and develop students around this, and to also develop infrastructure around this, so research. The project itself will develop new methods, procedures that will access and improve cyber resilience within Ireland. These methods can then be applied to other national digital systems of similar digital scale and complexity. Within sensor technologies, then, Tom would have also looked at the digital aspect within industry growing at, say, exponential rates, so creating new issues for industry. One such company that we partnered with this is ADI in Limerick, establishing a project around trust management within environmental sensing. The work was initially within the Confirm Centre, and it's now moved to 100% funded through ADI. The project has significant commercial interests and aims to develop secure crypto core that will enable a trust management system to deploy for ADI platforms in the future. The third one then is the aspect about mobile systems. So how do we secure mobile systems such as AGVs that you can see here? This is a project funded through Lero in partnership with Costal then, and it's looking at automated parts for automotive plant manufacture. The project developed a bespoke AIV. The hardware is developed through MTU Tralee, and the software control systems and the mesh systems were developed by UL through CRIS. The third one then is the Marai Centre. So this is aligned to these two projects. We looked at older infrastructure within industry. So how do you use, say, older infrastructure and try and bring them into new generation cyber secure systems? So we developed what's known as a bump in the wire system. That is a hardware software based system that can be simply plugged in to upgrade existing infrastructure within industry. Post-HSE ransomware attack and with other instances of cyber attack across public institutes, it's evident that there was a need for cyber upskill in Ireland and also a lack of infrastructure in the area. We got a significant infrastructure piece through HEA looking at cyber range and aligned then through both the academic side of UL and also the research initiatives within UL and within CRIS. The infrastructure itself is a mobile Airbus unit and is a unique system within Ireland. We use both cloud-based by Siren and the mobile unit is by Airbus itself. So the cloud-based system is ideal for learning and development, and the mobile system then facilitates testing in the event of a real-world action. Much of the research is closely aligned with new programs and new modules that are being developed across UL, such as the HCI program outputs and also the development of micro-credentials within that. I guess, you know, you can see there's a wide diverse of actions, real-world actions that we do in CRIS. We're always open to collaboration. We're looking for new PIs to come in with new ideas, maybe around, say, habitat monitoring. So, you know, we are open to bringing new people into the centre, and we're quite eager to do that.
Thanks, Chair. Do we have one quick question from anyone? No? Just, Chair, one quick question. In terms of the processing of some of that, like data and so on, does that happen on the drone, or is there like a base station that take care of that?
It depends on the intensity of the processing. So some of the mesh stuff, the point cloud, say processing, we do in the cloud. But say your detection system for detect and avoid, it's all done on the drone. The detect and avoid system is critical to safety, so it has to be. You can't depend on networking or cloud-based systems to be able to react in that way. So low-level stuff on the drone, higher level, say more intense systems on the cloud.
Classification, is that something that's automatic, or is that something that, you know, has to be manual after the bird species is identified?
When you look at that data, like within the industry, there's a lot of kind of, because we work with ESB, we work with Marine Institute and Green Rebel and some others to understand the industry, but there's no governance around that data. You know, they go out and survey, they say it's good data, it's not good data. They say it's 4 centimeter GSD, it's more like 12 centimeter GSD. And they're providing that to the industry, and the industry just, it's a tick box as a legal parameter, you know. So they're happy with that data. They don't really look at it. Someone comes along, they do annotation first. So they take one frame, they divide it into 30 frames. Someone scrolls through really slowly to see if there's any birds, and then identifies, clicks on it. Then that gets passed off to classification, right? So classification, they look at that blurry image and say whether it's a tern or a duck or whatever, yeah? But really, you know, we can't do full classification on that data. The people that are doing it, they're guessing, you know, so you can't automate that, you know. So what we're doing, what we have today is full annotation, or it's full segmentation. So it's the first step of it. So we can identify where the targets are, we can cut that image and we pass it on to classification. But when you look at, say, one survey is about 800 hours of manual processing, right? And 100 of those hours of classification, 700 are for manual, say, annotation, so trying to understand where the birds are. So we can do 7 of 8 of that data set. So it's quite good for the industry.
Really important.